It is my pleasure to introduce Dr. Wilmore Webley. Dr. Webley is a professor of microbiology and the Senior Vice Provost for Equity and Inclusion at the University of Massachusetts, Amherst. Dr. Webley will be discussing the evolution of the bird flu and the status of the bird flu vaccine. Dr. Webley, the floor is yours.
It's good to be with all of you. Where the influenza is concerned and even reporting on bird flu, PAHO, the Pan American Health Organization, has just started its own dashboard. I put the link in the chat for H5N1 in the Americas, and Peru does have cases, Ecuador as well, Colombia, certainly not on the scale that we're seeing in the rest of the United States and Canada, but certainly enough to be worried about. From Brazil to Argentina, Mexico, they all have cases there of the bird flu. When you get a chance, you can take a look at that. That's a live, active overall screen that you can take a look at. So essentially, what we're seeing is an interesting picture of where we are right now. What you're looking at is cases of COVID flu RSV combined for the week ending January 4th. And as you can see there, it's variable across different states in the United States. You're seeing some states like Arizona, New Hampshire, Minnesota, Wyoming having pretty high cases of all of these. When we break it out a little bit and look at it, you can see that COVID is very much up in many, many places. You're seeing it there. And so, again, we all want to live in a COVID-free world. As most of us have been saying, that's not going to happen. These are new COVID admissions to hospitals. These are flu admissions, RSV admissions. And you can see that COVID deaths, while it had gone flat, just start going up again. You're seeing wastewater numbers for COVID have started going up. So again, this is first week of January, off and running. Influenza-like illnesses have definitely started going up. And this dashboard here is interesting because it's showing you for influenza. This again is the week ending December 28th. And what you're seeing there is that you're seeing the different types or strains of influenza that are there. You're seeing, of course, influenza A, H5N1, dominating a lot, as well as H3s. And we'll talk a little bit about subtyping for those who might not be as familiar. And then a significant amount have not been subtyped for influenza A overall. And then, of course, you have some B lineage there that you always see that. In the next week coming up, we will see, I don't know that we've reached a peak yet, even though there's a drop there. It should be interesting to see what happens in the next few weeks for influenza overall. And so when we look at the trends here, looking at trend lines from 2020 coming back, what we're seeing is kind of interesting. You can see, 2021 was an interesting year because everybody was in because of COVID. We just didn't have that flu bump that we typically see December, January. But they came back in 2022 as people started going out. 2023, you're seeing that. 2024, and then now you're seeing right at the peak here, it's going up at a level that's very similar to what we saw at the beginning of last year. We're seeing now at the beginning of this year in terms of positive cases that we're seeing, again, with a similar type of breakdown of influenza A cases. So we're in for a pretty decent influenza-like illness season where all of these are coming forward. So let's spend a little time looking at influenza itself. Influenza, or the flu, is an interesting virus. It has these hemagglutinin and neuraminidase proteins, NA, HA, and it is the HA, the hemagglutinin protein, that binds to the sialic acid on our cells in the respiratory tract that leads to viral infection. And I'm showing you this because this is important as we think about vaccines and vaccine development and why we have to get a flu shot each year. So different species of hosts have different types of sialic acid in terms of the way the amino acids are shaped. And that actually determines host range for different strains or variants of the influenza virus. They're showing you other important proteins here, the M2 channel that is necessary for infection to take place. So this virus has 8 different RNA segments, an RNA virus. Inside of this shell, this outer membrane here. Inside of it, you have a matrix protein, and all of that, you have the nucleic acid. And the nucleic acid is RNA, and they code for 8 different proteins. These are proteins, the PB1 and 2 proteins are proteins that are helping the RNA synthesis, and PA as well, different segments of it. Your HA, again, is for attachment to the salic acid. Your NP proteins, again, for RNA synthesis, and then your neuraminidase is responsible for actually releasing the virus once infection happens. And the M1, M2 matrix proteins, and then these non-structural proteins that are actually responsible for some of the resistance to initial innate immune response, the interferon response, your type 1 interferon, that is really good at alerting nearby cells that an infection is happening. These proteins are obstructed. So again, the HA protein has 2 subunits, but it's made on one strand and then it is cleaved. And it is the HA1 portion that actually ends up binding to the sialic acid. So that's what you're seeing here on the surface, the HA protein interspersed with your NA protein for your influenza A virus. And in terms of nomenclature, these viruses are named by, again, the virus type. Of course, we have influenza A, B, and C are the main influenza viruses. Influenza A are the only ones that have led to a pandemic. So those are the ones that we absolutely have to watch. So when you see the full name of an influenza A virus, you will see it looking like this. And so A is the virus type. Then they have the geographic region in which it was isolated, and then the strain number, because as they find them, they number them, and the year of isolation, followed by the HA and NA subtype, because these are actually the variabilities. These are what change. So this is an H5N1 virus that's unique in the way it looks. And so there are about 18 different H subtypes and 11 different N subtypes. And again, you're seeing the influenza A, B, and C. There's a D that infects cattle. So we're not concerned about influenza C infects both humans and pigs. It has a type A and type B. And influenza B, like the Victoria and the Yamaguchi strains, infect humans. But again, our main concern is influenza A. So all of your outbreaks of H5N1s, H1N1s, all of those are all influenza type A. They infect humans, but of course they can infect a whole host of other animals, particularly swine and birds. We believe that influenza A actually originated in birds, in waterfowls, and that's how all of this started with these different subtypes. So the HA protein is really important because if you're going to neutralize the virus, prevent its entry, then you need to have something that's going to prevent HA from binding to the specific sialic acid. And I hinted that the HA binds to specific sialic acid receptors based on species, and the NA is also specific. So humans have alpha-2,6 sialic acid in the upper respiratory tract, which is where the virus typically binds. But interestingly, in the lower airway, right down in the lungs and the alveoli, you actually have an alpha-2,3. And pigs also have an alpha-2,6 and 2,3. And so birds typically only have alpha-2,3. So the receptor in the birds that it's binding to is alpha-2,3. And that's why we haven't seen human-to-human transmission of bird flu at this point in time, because it's used to binding to an alpha-2,3 receptor. In other words, the way the receptor looks to the virus is different. While it binds to human receptors, it doesn't efficiently do so. That's why you're not having this easy transmission. But it takes a few mutations to actually get it to actually adapt to binding to an alpha-2,6, which would be in the upper airway epithelial cells of humans, where it could readily bind and now start an infection that could be transmitted from human to human. And it doesn't have to be a type of mutational drift. It could actually be that you actually have what could happen in a pig, where you have an avian strain and a human strain coming into the pig, and because it has both alpha-2,6 and 2,3, you could actually have mixing, this crossover, and then you could have a new virus that has that capability to actually infect humans. And so you're seeing then that for different types of animals, it's mainly an alpha-2,3 binding that leads to infection. And so when you look overall at the picture here, it's kind of interesting because what you're seeing is this overall host interchange, we're having a whole host of transmission from the initial host, some type of a waterfowl, where we believe that the virus actually started in China, and then from there kind of just spread to different hosts with different salicylic acid composition. And you have these different mixings of hemagglutinin and neuraminidase, giving you everything from your H4N5 to your H7N7, your H3N2, your different backgrounds for different animals. And what we've seen over the many years is that it's not an unusual thing for a bird flu strain to get into a pig, and then that now gets into a human, as you're seeing here, leading to a highly pathogenic human strain like your H5N1 that now leads to an outbreak. So over the years, as people have looked at the different changes that we're seeing in these 8 different proteins, what became clear was that the major changes happened within the HA1, that's the binding protein, and the neuraminidase. So here you're seeing percent change in amino acid of the components, the subunits of your protein, and you're seeing here that this is where the major changes are happening. And this essentially is the reason why you need a new vaccine each year, because one can't predict what the HA and NA composition is going to look like and how that's going to play out. So that's essentially the immune escape for the virus. This is how it evades the immune response, by having these changes that come about, as I said, either through antigenic drift or antigenic shift. The antigen is the protein or the protein subunits that the immune system actually sees and responds to. However, not all proteins are immunogenic, right? Not all of the protein components are going to drive a strong immune response. Why? Because the virus very smartly covers a lot of these proteins with sugars, glycosylates them, right? And that is also true for the HA, that parts of it is highly glycosylated. And so for antigenic drift, what is that? That over time, as the virus replicates, most RNA viruses like this do not have a proofreading system. COVID actually has, SARS-CoV-2 has a proofreading system, even though it still makes a lot of mistakes, but influenza doesn't. So as it makes mistakes, as it's replicating, those mistakes cause what we call an antigenic drift, that over time you have a virus like this and it changes. So if you were vaccinated against it or you had an immune response against it, over time, those protein segments are no longer recognized by those initial antibodies, and so it's not as effective. It doesn't mean that other proteins on the virus that are recognized by antibodies and they're binding to it, but that neutralization that you're going to get from the HA and the NA, you're definitely not going to get it after you have this drift. So your body's constantly adapting to this changing protein composition. Now, if you actually have 2 different viruses, 2 different influenza viruses, so you have this human strain of influenza and then you have an avian strain, and they infect the same animal, in this case a pig, because that happens all the time, you could actually have the avian strain directly spilling over into humans, or you could have this mixing, this antigenic shift, leading to a new viral particle created. Because all they do is that they exchange these 8 segments. It's like you go into the swimming pool, 2 or 3 of you go into a swimming pool, you take off your clothes, you leave it on the ledge of the pool. You come out, you pick up person A, picks up person B's pants and put them on. So when person B comes out, they have to put on person A's pants. So now somebody who saw you walking over there, they might think that you're somebody else, or, you mix and match the shirts or the hat or whatever is there. That's essentially what's happening here. So you can see the color differences here, that the avian have these purple ones, the human have these blue, but now you're actually having purple and mixing with blue, and now you have pink. So this recombination event that happened create a new virus, and this new virus now can lead to a pandemic. Why? Because nobody has any response to it. Nobody has any pre-made antibodies, any immune response that was made against it. And that's essentially how we've gotten new strains of influenza over the years, leading to new pandemics. They're essentially similar viruses that just picked up new capabilities. So, for example, the 1918 flu pandemic was an H5N1 virus strain. And then you actually had the 1957 flu outbreak, the Hong Kong flu, was an H2N2. But then you had the 1968 outbreak, it was an H3N2. It got that N2 from this N2, right? And then you had another H1N1 flu outbreak in 2009, which was a little bit of a variation from the 1918 H1N1 because they changed over time and picked up different components. And this is how influenza works. And this is how you can get a new flu pandemic. So while people are worried about an antigenic drift for the current bird flu, in this season, when I showed you that overall influenza numbers are up because we're in flu season, I'm actually more worried about what I showed you here, an antigenic shift, where one could get infected with the bird flu, and then with the current human flu strain that we're having, the H1N1, and that now could spill out a new bird flu strain that's a recombination, and you now have a pandemic on your hands. It could be as simple as that. Just two strains of the circulating regular flu season flu plus the bird flu that we're seeing in this season. And that could be problematic. So that's more my worry than having an antigenic drift and a mutation that now gives it capability. So let's talk a little bit about this bird flu that we're dealing with now. This strain of bird flu that we're seeing now started in 2003 to 2005. This H1 spread started in China, went through Asia. They saw it in poultry farms, killed a lot of poultry in Africa, in the Middle East, in Europe. And over time, they saw different clades started popping up. And then in 2014, 2016, there was this H5N6 and H5N8 outbreak. And again, that H5 gene swapping actually happened that stage. And so what you had is that you had these wild birds that emerged with these new strains, and it developed this clade of the 2.3.4.1. But then you had this 2.3.4.4b virus strain in 2018 to 2020. And that's the clade that we see right now that's spreading around. And so this same clade is what we're seeing in the United States and Canada that's leading to bird flu in animals, in cattle, and the bird flu outbreak that we've had. And you've probably seen the numbers, but what I want to show you here is that for the first time in 2023-24, we actually had this strain of bird flu expand, significantly expand, to infect several other types of animals all over the United States that had not been infected before. Everything from your wild cats to domestic cats to bear, wild canine, raccoons, skunk, opossum, you name it. And the USDA has been keeping track of this. I just pulled this a few days back, and you can see this is all over the country, and you're seeing different types of animals, new animals that had not been infected before, being infected now with this strain of the bird flu. And of course, you would have seen that it's infected cattle in a way that we hadn't seen before. And over again, we've seen these lead to human infections. And some of these infections have been mild. Others, initially, people had respiratory tract infections. But for the most part, people had pink eye, where it infected the eye rather than the respiratory tract. But we now know that it can infect the respiratory tract. And it's kind of interesting because when you look at where you have bird migrations, the genetics screening show that this clade is coming directly from birds into cattle. It's changed a little bit in cattle, but it really is from birds. And this is looking at bird migrations across North America. And what you're seeing is that this is actually going over a lot of the areas where you have a lot of chicken production and a lot of farms as well. So no wonder we've had this huge culling of cattle, because you're seeing in the different areas here, like the Mississippi, that yellow area, the purple yellow area, central and Pacific areas overlaying there. And this diagram from Ohio State is showing that the chicken that we eat, the chickens that we're using for eggs, They're right underneath where this migration of wild birds, including your Canadian geese that love to make multiple stops along the way, including in people's backyards. And that's how you're having the transmission. So you're having birds, wild birds to cows, then you're having cow to cow transmission. You're also having cow to poultry transmission and cow to cat transmission. We've seen that on farms where we had these outbreaks. And then we saw cow to human transmission. We realized that that was coming from milk, probably other things there. And then what we haven't seen, which is good, is that human to human transmission. But they've picked it up in raw milk, in pasteurized milk. They've seen the nucleic acid, but it's not alive, so that nobody's been able to grow it from there. But this continues to be a worry. California right now has the highest numbers of bird flu in cattle, and that continues to be a challenge. And so, as I said, it enters people's eyes, their nose, their mouth, and of course you see the many different ways that the cattle can spread it. But what we also found out is that a lot of times it's being transmitted by these workers who are working on the farm, and also by the trucks that they're using to transport the cattle. Many times it turns out that they end up contracting with the same company, and they're not sanitizing or washing or cleaning effectively these vessels as they're moving animals back and forth. So there's a lot of areas there for contamination. And so Kevin mentioned at the top that a lot of cattle, a lot of poultry have had to be culled. You can see here in the last 30 days, they've had to cull 10.74 million, but 134.8 million birds have been affected with this highly pathogenic H5N1 virus. And you see that backyard flocks, commercial flocks have been affected and continue to be affected over time as you look over the years. And we're looking to see what's going to happen. So what's the current situation in the United States for this year right now? Number of birds detected, over 10,000, nearly 11,000 in 52 different jurisdictions, different counties, over 1,000 different counties affected. We've had 67 totally confirmed human cases of H5N1 and one death. That patient in Louisiana who apparently caught the virus from birds that he had, wild birds that came into his backyard flock. We know that this person was older, they say over 60 or probably over 65, but seemingly healthy enough to be in the backyard and just never recovered. It turns out that the same subclade that he had was the same subclade that a teenager in British Columbia had, who got really, really sick and almost died and recovered after many, many, many weeks or maybe months. So again, no person-to-person spread, but certainly a problematic challenge that we're seeing here with the bird flu. And as we look at over time, this is a timeline graph showing you the spread of bird flu starting from 2023 in October until the end of December of 2024. And you can see that you have avian strains, you have mammals, you have cattle, and then, you know, out here in California is where at the end of the year we saw an explosion of both avian and cattle infections, and of course some human infections from the cattle. So that orange that you're seeing is cattle, and the blue was human. And so what has the US been doing? They've been stockpiling bird flu vaccine for poultry. Of course, it is not the current strain that we have, but it should be good enough. In fact, if you've gotten this year's flu vaccine, it should offer some level of protection against the bird flu. Clearly not full protection, but some protection. And so the US has been keen in trying to build the stockpile, essentially the antigen, in vials like this, with the intention that, okay, if this ramps up and becomes a pandemic, then we'll be able to deploy it to people who are working directly with birds or in areas where they're most vulnerable. But I don't think we have anywhere close to a stockpile right now that we could deploy to the general population if some big outbreak took place. So there are 3 different bird flu vaccines. And you might have known that in Europe, they actually started giving this to farm workers, people who are working directly with cattle, because of what was happening in the United States. And it's a Seqirus that they're actually giving. This again is an inactivated vaccine against H5N1, not the exact clade of H5N1 that we have circulating right now, but it should be good enough. And then you have another H5N1 by GlaxoSmithKline that is ready to go as well. And then another Sanofi Pasteur vaccine. This is also for people 18 to 64 years old who are at risk for exposure to the virus. So there are some tools there in the toolkit. These vaccines have been licensed for a while. They've been sitting there, and the US has been looking to put monies in place to surge that. But again, Europe, not only in Finland, but in other countries, have decided that they're going to go ahead and actually start vaccinating people who are vulnerable. And at the same time, Moderna has been working on an mRNA vaccine for influenza, looking at trying to protect against the current strains that we have. I think they're looking at a multivalent vaccine. In other words, looking at all of the H5N1 variants that we have and putting all of that into one vaccine so that you'll have full coverage overall. The Health and Human Services is also looking at producing an mRNA vaccine. They have gone ahead and BARDA has invested in this. Most of these trials are actually in phase 1 clinical trial at this point in time, so nothing even close to hitting the market. But at least there is some momentum in doing this. We don't know what the new administration will do where this is concerned, if they will take this as seriously. But the whole idea is that they have started surging manufacturing capabilities. The current egg supply is a concern because a lot of these vaccines that I showed you need eggs to ramp up the production of these vaccines. So an egg shortage is not a good thing for planning for vaccine upscaling. The current 2024-2025 flu vaccine composition is a trivalent vaccine. Whether you're doing the cell-based recombinant vaccine or the egg-based vaccines, it has 2 strain type A viruses in there, H1N1, H3N2. The H1N1 is the one that you see surging most. And then it has a type B, the Austrian strain in there, the Victoria strain. And so this is the composition of the egg-based vaccine, which is a common one that we get. Then you have the recombinant cell-based vaccine. This is for people who are allergic to eggs, for example. They can get this type, that is a recombinant vaccine, having similar types, but this has the Wisconsin strain, Massachusetts strain from 2022, and then of course the Victoria strain overall. So it has both type A, type B influenza, and that seems to be able to give probably about a 40% coverage. Of course, none of these vaccines have given anything more than a 60 or 65% protection over the past decade. We haven't had any of these flu vaccines that have reached anywhere above that. But when we look at the vulnerability of the virus and where one can tackle it, one of the big things that the US and other regions have been looking at is a universal flu vaccine. It's an acknowledgement that this virus changes all the time. And the question is, can we come up with a vaccine that is able to work whether or not you have a strain change, an HA or NA change? And that really is the holy grail of vaccine. It's the same thing for COVID. Can we get a vaccine that's made against a constant region of the virus that is not changing all the time and still offer the level of protection that we need to neutralize? And so this is not just vaccines. Of course, there are vaccines in the mix, neutralizing antibodies that bind to these regions of HA and NA, but they're also developing medications, which I think is also very important. These enzyme inhibitors, the ursolidase that cleaves off sialic acid so that the virus doesn't bind effectively to it. Your neuraminidase inhibitors, which means that if you give a patient these, then the new viral particles cannot be released from the infected cells because it needs your NA protein in order to do it. If you inhibit that, then that won't work. And these are the drugs that are there. Some of them have been tested, have been shown to work. Viral genome inhibitors, that it cannot complete its replication of its genome. In other words, you're having inhibitors of the polymerase, inhibitors of translation and transcription of proteins. And so a complete wraparound 360 of what is the virus doing, where are its vulnerabilities, what can we do to stop it at specific stages, preventing the HA from unwinding. It actually has a mechanism where it has to unwind in order to do its job. If you can stop it there, either with an antibody or with a drug, then the new progeny will never be able to bind to the sialic acid to come around. So this universal flu vaccine is something that they continue to invest in. The latest iteration is an interesting one where they've used computationally optimized broad reactive antigens that they call COBRA, using immunoinformatics essentially to design HA and NA antigens or immunogens that they can put together. But what they've done here is that they've gotten 8. So this is an octavalent vaccine combination where they've gotten NA and HA proteins from the most common ones that infect humans. And they've put all of that together into this recombinant design. And in animal models, this has worked very well. They're using the seasonal as well as pandemic strains. And so fingers crossed, maybe they'll come up with something that they're able to put into clinical trials. Here's another block where they're actually using the HA protein. What I showed you was the outer leaf part of the HA protein is what the current antibodies are built again. What they're doing now is that they're stripping it off. You see this headless HA. They're stripping that part off and just leaving the stem, because the stem is constant, right? The stem doesn't change. You can't change the stem. It needs that constant there. And they're using that now to make vaccines, including an mRNA lipid nanoparticle vaccine that they're throwing that headless HA on to see if that now would become a universal vaccine platform. So very, very interesting overall. And I'll essentially stop there so that we can take a few questions.